Assalamu alaikum wa rahmatullahi wa barakatuh, and welcome to today's edition of the VOC Matric Revision Program. And yes, we are covering physics today with our facilitator, who is Muntasir Kadri from Intune Tutoring. And today, on the physics topic, he will be speaking about or sharing some insight on the Doppler effect. Assalamu alaikum, Muntasir. Welcome to today's session.
Wa alaikum salam. Shukran for having me.
Is it Doppler or Doppler?
Doppler.
Doppler, okay. So, yes, I'm quite curious to find out what this is all about. I actually did physics in Matric, and that was in 2003. And really, my memory is, I'm not sure if we covered this topic in physics. Is this like the higher grade in physics?
This would be your higher grade in physics, yes.
Physics,
So
okay, okay.
yeah, so the Doppler effect is actually something we experience every day.
Okay,
So
interesting.
yeah. So if you've
Wonderful.
ever
I'll
been
be,
in your
yes,
car and you have a motorbike speeding past you, and you hear
yes.
that meow, that's the Doppler effect in action.
Oh, okay, interesting. So I'm
Yeah.
really going to be listening attentively to today's session because, as you explain now, we experience this on a daily basis, especially when we are commuting or driving in our vehicle. So I now hand over to you to proceed with today's lesson.
Okay, shukran. Okay, assalamu alaikum everybody. So as per introduction, we will be covering the Doppler effect. This will be in question 6 of pretty much every exam. So most exams have a standard layout, and question 6 is usually the Doppler effect. So the Doppler effect it's not too difficult. It's usually a perspective based type of question. So it's either from the perspective of the listener or observer and the perspective of the source. Right? So of course you need to be able to shift perspectives to understand this problem. So just a quick introduction. If we look at the Doppler effect over here, right? They usually give you examples involving sirens or motorbikes, and it's always got to do with sound and frequency. Okay? And then this is the general formula that we will be using, where we have the frequency of the listener is equal to the velocity plus minus the velocity of the listener over the velocity plus minus the velocity of sound. And then we times that by the frequency of whatever the source is. Okay, and of course, this equation changes depending on what perspective we are working with. If we're working with the perspective of the listener, we remove the plus minus Vs and we just leave it as V or plus minus VL over V times Fs. But if it's from the perspective of the source, we remove the velocity of the listener. Right? And that is how we'll basically go about it. So let's jump straight into the first question. So question 6. A learner in a car moving at a constant speed of 10 meters per second along a straight horizontal road records the frequency of a sound emitted by a distant stationary object. So it's very important to note the object is stationary, and the only thing moving is the observer. The learner then repeats the recording of the frequency of the sound when the car travels at a new constant speed of 20 meters per second. The graph below, not drawn to scale, is obtained from the results. So we just quickly analyze the graph. We can see on our y-axis, we have the recorded frequency in hertz. And on our x-axis, we have the speed of the car in meters per second. And if we just analyze this quickly, we can see that here the speed of the car is 0. So this means that the speed of the car is not moving, so the car is stationary and it's in line with, it's basically in line with the object. So we can say that where it's stationary, right, the frequency is 700 hertz. And here we see the cars, okay, the speed is increasing, right? And we can see the speed has now reached 10 meters per second, and now the frequency is 679. So here we have a decrease in frequency. And as we carry on, the frequency decreases. So this should already intuitively tell us something important about what is occurring. And what that is that we can tell immediately that the car is actually moving away from the source. And this makes sense because what's happening is the wavelength is increasing because we're getting further from the object. And if your wavelength increases, that means your frequency decreases. Okay, and that's exactly what's happening here. So immediately we can tell the car is moving away. So the first one is we need to state the Doppler effect. Okay, the definition of the Doppler effect, we'll just look at that over here, is the change in frequency or pitch of the sound detected by a listener because the sound source and the listener have different velocities relative to the medium of sound propagation. Now, the medium of sound propagation would be what? That would be air, right? Because sound is being propagated in air. Sound requires the matter to be propagated. This is why you cannot hear anybody scream in space, because space um, is unable to propagate sound. The other definition they give you, which is much simpler if you want to remember, is this one: an apparent change in observed or detected frequency or pitch as a result of the relative motion between a source and an observer or listener. Okay, so very, very easy to understand. So we can just bear in mind that there's a change in detected frequency. It's all relative to the motion, right? And the reason they use the word relative is because it depends on whether you're looking at it from the observer's perspective or from the source's perspective. And that's why they state here between a source and an observer. Now, the next question, 6.2. Use the graph to answer the following questions. Write down the frequency of the sound emitted by the stationary source. Well, we actually spoke about this earlier and we found that it's actually 700 hertz. If we look here, this is where the car is stationary, and this is also where the source is stationary, right? And here we can see that it's at its maximum frequency, which means we are right by the source. We are basically in front of whatever is making the sound. Okay, next question. All right, and they say give a reason for your answer. And they say, yeah, learner or observer listener velocity speed is 0, which is what we mentioned. Right? So listener and source both stationary. 6.2.2. In which direction is the car moving relative to the source? Choose from towards or away. Well, we have mentioned that the car is moving away from the source. And why is it moving away? How can we tell that? Well, because the frequency is decreasing as the car speeds up, which tells us that the car is moving away from whatever the source is. Now, the next question is calculate the speed of sound in air. Okay, so we have to now use that formula that we looked at, which was this one over here, right? So we have the frequency of the source. We've discovered that it's 700 hertz. Then there's the frequency for the listener. And then we have these speeds given over here. And this V here would be the speed of sound in air that will need to be calculated. Okay, so if we go to the memo over here, you'll see they'll use that equation. There we state it away. And there we go. This is the equation they selected. Now, if we look, they select to use for the listener. And why do they do that? Well, if we look at the graph, it makes sense that we select for the listener because the relative information that's given to us is that of the speed of the car. We know that the source is stationary. So it makes no sense to use the source in the equation. Okay, so now we have the speed of the car, we have the recorded frequency, and we can go ahead and input the data. Okay, so now let's just do it like this. I'll just grab this equation over here. All right, we'll add it on a new page and let's give it a try. Okay, and yeah, we'll grab this information as well. Give me a second. We need this graph. Add it here. And let's just take the question as well. Here we go. Right, and this is for 5 marks, but it's not that complicated for 5 marks. So we have this equation, which will usually be given to you on your formula sheet. Right, and now we go ahead and we try to solve for the problem. So we can state, let's first do some Sherlock's homework and we investigate and we get the information we need. So let's first state that the frequency of the listener is equal to the speed of sound in air plus the velocity of the listener divided by the speed of sound in air times the frequency of the sound. Now let's get our data together. What is the frequency of the listener? Well, it depends on what speed we decide to select. You can select 10 or 20. Wouldn't be advisable to select 0. That would make no sense. So let's just select the maximum value they give us. We can say that the frequency of the listener at 20 meters per second is 658,2 hertz. We can then see that the speed of the listener is 20 meters per second. We know that the frequency of the source is 700 hertz. And now we need to solve for the unknown speed of sound in air. Okay, now we go ahead and we substitute our values in. So we get 658,2 equals this plus 20 over speed of sound in air times this frequency over here. Okay. Now we go ahead and we do some algebraic manipulation. So what do we do? Well, we can see that the 700 is multiplied by this entire term here. So we divide the 658 by the 700. And where is my calculator? Here we go. So I'll just input this here first. So what I'll just do is I'll write this here. So we got 658,2 divided by 700 is equal to V plus 20 over V. Now, we say 658,2 divided by 700. Right, we get a value of 0,94. So let's use this over here. Right, is equal to V plus 20 over V. Just move this out the way. Okay. Then we just multiply. We're going to get rid of this denominator. So we're going to end up with 0,94 V is equal to V plus 20. Okay. Now, what do we do from here? Well, if we look at the memo, let's get this up over here. Right, okay. So important piece of information. This is what I figured. I made a little error on. So we need to determine whether or not we need to use plus or minus. So of course I can see here, if I look at what I set up over here, if I must use plus, I'm actually going to get a negative answer, which is incorrect. So how do we know whether from the get-go whether or not to use plus or minus? Well, let's just take a look here and I'll show you. So here they state, if the source moves towards the listener, then Vs is negative. So we know the source isn't moving. So here they say, if the listener moves towards the source, our VL, we will select positive. If the listener is moving away from the source, our VL will be negative. And we know that according to this problem, we found that the vehicle is moving away. So this positive needs to actually be a negative. So let's go ahead and change that. All right, remove this. We rectify everything. And now we will get a positive answer. Right. There we go. Now, do some manipulation. We move the V, the 0,94 over. Right, and we'll end up with 1 minus 0,94. And that will give us an answer of, I'll just make an arrow here so you can see where I'm going with this. This will be 0,06 V is equal to 20 meters per second. Now we just divide 20 divided by 0,06. And that gives us an answer of for the speed of sound in air is going to be 333.33 meters per second. And there we go. That should be our final answer. And that's for 5 marks. Right? So very important. Note to use this equation. Know that if the observer or the listener is moving away from the source, we select negative. If the listener or observer is moving towards the source, we select positive. Right? And that's really the most intricate part of this equation. It's just knowing whether or not to select negative or positive, and also knowing whether to use a listener or source. Okay? Now we can go back here, we can take a look at the memo, and there we go, we have the exact same answer. Okay, moving on, let's go on to the next question, which is example 2. So, once again, they love asking this definition. We've already looked at it. State the Doppler effect in words. Okay, and we know what that is. It's got to do with the relativity of sound and the motion of two objects. Right? That's just a basic idea with regards to it. There is a more formal definition that we looked at, and if you want again, we can look at the formal definition again one more time. The change in frequency of both pitch or of the sound detected by listener because the source and the listener have different velocities relative to the medium of propagation. Okay, so all you need to know is important words: change in frequency, okay, detected by listener because of the source and the listener having different velocities. That's the other important thing. Different velocities relative to the medium of propagation. Okay, back to this question. Yeah. So let's look at this graph. So they say the siren of a train moving at a constant speed along a straight horizontal track emits a sound with a constant frequency. A detector placed next to the track records the frequency of the sound waves. The results obtained are as shown in the graph below. So here, this is a reverse of what the previous question was about. In the previous question, the listener was moving and the source was standing still. But in this question, the source is moving and the listener is standing still. So, if we look at our table over here, we are given two variables. We are given time on our x-axis, measured in seconds, and on our y-axis, we are given frequency, measured in hertz. Okay? We have a time of 0 seconds, and we can see that at time 0, which is basically where the train and the source are aligned, we have a frequency of 3,148 hertz. Okay, so that means they are both directly in the same area relative to each other. And as you move along the graph, as time goes on, we see that the frequency drops to 2073 hertz, meaning that the train is now moving away from the listener. The source is moving away from the listener. 6.2. Does the detector record the frequency of 3,148 hertz when the train moves towards the detector or away from the detector? Well, if the train is moving, if we imagine the scenario, we can go here, open a new page up. Let's imagine the scenario. It's always good to conceptualize these things. I always tell the students, conceptualize, conceptualize, conceptualize. It's very important. If you can imagine what is going on, it will make things so much easier for you. So let's say that our detector is over here. Here's our detector. Maybe it's some box that's picking up the sound. Right? This is the detector. And then over here in front of us, we have the train. Now we can imagine that, let's say the train is over here. Okay, this is going to be a horrible looking train, but let's say this is our train, right? And we can see that our train is moving towards the source. Now, as we learned previously in the other question, right? And we'll just keep adding on. Right, there we go. Right. So what's happening? If the train is giving off some sound, right? Here's our sound waves, right? And our sound waves, here we go, it's going off. right? We have troughs and crests, and it's moving, and as it's moving, right, it's going to give sounds that are going to hit this. So we can see here that, oh, maybe I should be more accurate with this so you can get a better understanding. Let me just erase this. And I'll just use a different color as well. So if you look here, right, so this is closest to the train. Look here. And as the waves move further and further from the train, we can see that the wavelength is increasing, which means the frequency is decreasing. So at this position, we can tell that the frequency is smaller than over here, where the frequency is directly by the box, right? And we'll end up having basically a higher frequency hitting the detector. So according to this question, we can state that, well, the train is moving towards the detector. If we go here, there we go, towards the detector. Next question. Calculate the speed of the train. Take the speed of sound in air as 340 meters per second. So we grab this, we'll add it on a new page, we'll put that there. We'll get this over here. We'll add this to the current page, and we'll go ahead and we try to solve this. And then we'll just get this equation over here. I would like to copy it. Okay, that's fine. So, here we go. I'll just do this. Go back here. Here we go. Okay, now let's try to solve this. So they want us to calculate the speed of the train. So we have information about frequency. We have information about time. So let's do some hunting. What information do we have? Okay. Go back here. Okay. Do they give us anything else? No, they don't. Give us this information about time over here. Okay. Now, let's take a look. So they go ahead and they use this equation, as we can see here, which is what we're going to do. And then we have to take the frequency of the listener and the frequency of the source. Okay, and we have V over V minus Vs. So we know what's happening is that we can state that, well, the train is moving towards the source, right? But in this case, we don't really have any information about, we do have information about the speed of sound in air, right? We know that the source is, the listener is standing still, so that's just going to be plus 0. So we can go ahead and use this equation over here. Now notice, they are selecting negative. Okay, so if you look here, there's two values, 3148. They select negative. Why? Because the train is moving towards the listener. And here they select positive. Why? Because the train is moving away from the listener. So notice how it's reversed. Okay, compared to when it is the source, compared to when it's the listener that's moving. But in this case, the listener is standing still. So we can go ahead, pop this open here, and let's just input the information. So we know the equation is, oh, sorry, let's just go back to the memo over here. So here we end up with this. We say 3,148 hertz, which actually comes from this over here, which is where the train's moving towards the source. And then over here, we have 2073 hertz. And they select that one, and that's the frequency over here. Once the train is now moving away from the listener, sorry, not source, train's moving away from the listener. And then we end up with these two equations. Now, what do you think we are able to do here? Well, something very interesting arises. We can actually use simultaneous equations. We can now set these two equations to equal to each other because the frequency of the source does not change. It remains the same, right? So if we go here, you'll see that they set these two to equal to each other. So how did they get that? Well, I'll show you. Let's just grab this information from the memo, all right? And I'll input the information that is missing. So this makes a little bit more sense. we could have this, add it to the current page. Oh, page. Yeah, we'll just add it to a new page, actually, it's fine. Add it to a new page. Now let's take a look at this. What's happening here that's missing? Maybe it might look a little bit confusing. Well, let's take a look. So what they did was they rearranged these two formulas, and this is how they did it. So here they made the frequency of the source the subject of the formula. So you'll actually end up with Fs is equal to 3,148 divided by 340 over 340 minus Vs. Now, notice it is a fraction over a fraction. This can be written as 3,148 over 1. And as we know, when we divide fractions by fractions, there's that little trick where we swap the numerator and the denominator, and we multiply it by the other fraction. So this actually ends up looking like this. 3,148 times by the 340 minus Vs over 340. And that's exactly what we have here, right? And the exact same thing applies with this one over here. So I'll just take this over here, and we'll just end up with Fs equals 2073 divided by 340 over 340 plus Vs, speed of the source. Okay, and then if this gets rearranged, it's just going to be 340 plus Vs over 340. Now, we have Fs and Fs. Well, we know that Fs is equal to Fs, so therefore we can put the two equations together. And then we end up with this over here. And then when we do the calculations, you'll find that Vs is equal to 70 meters per second. So let's go ahead and do the calculations, just so I can show you how they go about to solve this. Okay, so I'm not going to rewrite this, but we'll do the calculations from here. So we can just say, well, 3,148 times 340, what does that give us? Let's take a look. That gives us a massive value. I just want to see if there is a way we can negate having to use and get such a massive value. I don't believe there's any. I mean, we could divide this by 2073. And then this gets divided by 2073. It would shrink the value down and make things a little bit easier. Okay, well, let's just go ahead and do straight multiplication and expand it normally. So if we expand this normally, we'll get 10,70320 minus 3148 Vs over 340 is equal to, and we can go 27.3 times 340. It gives us 704,820. So we're going to get 704,820. All right, and plus 27.3 Vs over 340. All right, we can do that. Now, what's the next thing that we do? Well, we have them both over 340. So therefore, we can actually just ignore the 340s. Okay, because there's many ways to go about it. I mean, if you want, we can just go, well, we can just multiply this by 340 and multiply this by 340. By doing that, we're not changing the value of the entire equation. So that's fine, right? Or we can just ignore it. We go, okay, it's the same denominators. We can ignore this. That's not a problem. So we can ignore these. right? And then our equation ends up looking like this. Okay, now we go ahead and we can actually solve for this. So if I go 10, 7, 0, 3, 20 minus 7, 0, 4, 8, 2, 0, that gives me 3, 6, 5, 5, 0, 0. Right, and this is equal to, and I'll just add this onto that over there, 27, that's a 7, 3 plus 3, 1, 4, 8, gives us 5, 2, 2, 1 VS, and then we just divide. 365,500 divided by 5221, right? And this gives me a value of Vs is equal to 70 meters per second. And there we go. That's how you go about solving this problem. So Doppler effect problems are not too complicated, but as you can see, there are, well, we've got so far two types of ways that they can ask this problem, right? And it also depends on the variables they give you. In the first problem that we looked at, if we go back here, they told us that the observer was moving and the source was stationary, right? And we had to go and figure out, okay, which one is negative and which one is positive when looking at the equation. And we discovered that, well, if the listener is moving away from the source, this is going to be a negative value. But if the listener is moving towards the source, it's going to be a positive value. Then in this problem over here, which was quite different, we looked at the fact that the source was moving and the listener was standing still. Okay. And we discovered that if you look at these equations up here, let me just get my laser pointer. There we go. If we look at these two equations over here, we can see that for this one, the source is moving towards the listener, and there we make it negative. And here the source is moving away from the listener, and here we make it positive. So we can see it's different for listener. It's the opposite for listener and source with regards to how we selected these over here, right? So it can be a little complicated. You need to remember that. I mean, and if you look over here, you'll see it actually that they tell us source moves towards listener, negative. Source moves away from listener, positive. Listener moves towards source, positive. Listener moves away from source, negative. So it depends on the perspective you are looking at, whether we're going negative, positive, or positive, negative. Okay? Then, the other little trick that occurred here was, well, they wanted us to calculate the speed of the sound of the source. They didn't give us any relative values like the previous one with regards to the speed of the objects. Right? We didn't know the speed of the source at all. They asked us to calculate that. And it's important to note that the frequency of the source remains the same, regardless of whether it's moving or not. Right? It doesn't change the fact that the siren is still pushing out sound at the exact same frequency. It's just that the frequency may change relative to our position, but the actual frequency of the actual siren remains the same, right? And that's why we ended up with this. And we could manipulate the equation so that the frequencies of the source became the subject of the formula. We then rearranged it, and we could set these two things to equal each other using simultaneous equations. And then we ended up with calculating the velocity of the source. So a bit of a tricky one, but not impossible to solve. Okay. So I hope that helped you somewhat with the Doppler effect. And I hope you don't get thrown off by problems like this. Just remember those important key points that I iterated right there. And yeah, everything will be okay. Right? So not the most complicated section. You should be able to get full marks for the Doppler effect in your physics paper. Okay, so that is us for today. If you would like to access these notes, it is available on the Intune website. I'll just show you over here. You just go to intunetutoring.co.za right there. Okay, you can just go to VOC radio tutoring over here. You select that tab, it pops up. and you will see all of these available. And here's the latest one, the Doppler effect. Right? So all of these are available. These are all the chapters that we've gone through so far for physics. Here's the mathematics sections that have been gone through so far. And if you need to go over these questions or you just want to revisit the problems, they are available to you here. All right. So that is it from me for the day. I hope you enjoy the rest of the day and that this was helpful. Assalamu alaikum wa rahmatullahi wa barakatuh.
Walaikum salam wa rahmatullahi wa barakatuh, and that Muntasir Kadri from Intune Tutoring will actually link to the free notes onto this recorded session. Remember to like and share this afternoon. Everybody, farewell. Assalamu alaikum wa rahmatullahi wa barakatuh.